Everyone, today we are going to see about Theorem D. If EI is an orthonormal set in the Hilbert space H, if an x be an arbitrary vector in H, then x minus summation x comma EI orthogonal to EJ for each j, which means Z orthogonal to EJ, Z comma EJ is equal to 0. So we have considered the set that EI x comma EI not equal to 0. Then the following cases arises. The case 1 is empty and the case 2 is countable. So for empty, x comma ei equal to 0. So z equal to, we take x minus summation x comma ei into ei is z. So if x comma ei equal to 0, our z equal to x. So we proved that z comma ej equal to 0 and x comma x equal to z. So x comma ej equal to 0 by 1, it is true. The next case 2 is S is countably infinite. Let the vectors S be arranged in the definite order. So S be the countably infinite means the vectors are arranged in the definite order. S equal to E1 to En. Sn can be written as summation n equal to I equal to 1 to n x comma ei into ei. For some m greater than n, Sm can be written as summation I equal to 1 to m x comma ei into ei. So norm of s comma sm minus sn the whole square can be written as norm of summation I equal to n plus m x comma ei into ei the whole square. This term can be written as up to s m minus n means I equal to n plus 1 to m x comma ea into ei the whole square. So it will be come as inner product summation I equal to n plus 1 to m x comma ea into ea summation j equal to n plus 1 to m x comma ej into ej. So if we take summation out means x comma ei into x comma ej bar x comma ej bar is taken from the second form. So ei comma ej equal to 1. So it will be norm of x comma ei the whole square. By Bessel equality, the series n equal to 1 to infinity is convergent and m comma n tends to infinity, and this convergence term also tends to 0. So norm of Sn minus Sn square tends to 0. So Sn is the Cauchy sequence in H and H is complete. H is the Hilbert space. So it is complete. The Cauchy sequence Sn must converges to some. It is a complete means the Cauchy sequence Sn must converges to some vector S in H. S equal to summation I equal to 1, n equal to 1 to infinity x comma en into en into en. So we define that summation x comma ei into ei as summation n equal to 1 to infinity. We define s equal to 1 to infinity en x comma en into en. So summation x comma ei into ei as n equal to 1 to infinity x comma en into en equal to yes. Okay, then we take that x minus summation x comma ei into ei comma ej. We take this term and we have to prove that this is orthogonal. So for that we take this term and multiply means x minus this term is known as s comma ej. So x comma ej minus here is limit of sn comma ej. So x comma ej minus limit of sn comma ej. If ei not belongs to s means so that x comma ej equal to 0. X comma ej not belongs to s means x. If x ej not belongs to the s term means x comma ej equal to 0. So Sn comma ej equal to Sn comma ej can be written as Sn is summation n equal to I equal to 1 to n x comma ei into ei comma ej. So x comma ei comma ej will be definitely 0 because x comma ej is equal to 0. So the limit Sn is equal to 0 and the limit Sn comma ej is 0. So limit Sn comma ej equal to 0, this term will be 0. Second, we take this for each j. Ej belongs to s. X comma ej not equal to 0 means we take that Sn comma ej. We take that Sn comma ej. Sn comma ej as for Sn summation I equal to 1 to n x comma ei into ei comma ej. We get x comma ej. Okay, x comma ej. So limit xn comma ej goes to, we substitute the limit sn comma ej, it will goes to that sn comma ej is goes to x comma ej. This limit term is goes to x comma ej. So x minus summation x comma ei into ei comma ej. This instead of e we have x comma ej as it is, minus for limit sn comma ej we have x comma ej. So it will be 0. X minus summation x comma ei into ei orthogonal to ej for all j. Hope you all understand, and thank you.